Okay, start the recording here. So on the previous example, in regards to so what this is, we're continuing on. We're going to look at another example from section 4.3. But I had a question here about for the rational function that we just used calculus to help us graph that function. When we looked at the concavity, when we looked at the second derivatives, when x was equal to -1 and when x is equal to +1, the second derivative was equal to 0. And we knew that those were points of inflection. But what I want to ask you is, what does it mean for when a second derivative is equal to 0? Okay, how do we interpret that? Well, let's look at the graph. We drew the graph using calculus. Let's look at x equals -1 and 1. Okay, what I want to do is at -1 and 1, well, I was debating about this. I'm focused here. I'm looking at my function when x equals -1 and when x equals 1. And what I guess I'm going to ask here, I'm going to draw tangent line there. A tangent line there. I can probably make this. And so you notice that our function is not linear, right? The function x squared over x squared plus 3, that's not a linear function, right? But when you're at the inflection points 1/4 and -1/4, and that's remember for this example, that's where the second derivative was equal to 0. What does that tell you about the function right there? Is the function nonlinear or linear right at those inflection points where the second derivative equals 0? Does the function appear to be at that moment, at those instants, when x is -1 and when x is +1, when the second derivative is equal to 0? Does the function, it's linear. It's linear right at those moments. That's right, Ian. And the way you could sort of think about that is if you take any function, okay, you take any function like f of x equals mx plus b, right? We know that all lines have this form, y equals mx plus b, where m's the slope and b's the y-intercept. Okay, so this is now separate from this example. But I'm just trying to justify the comment that I just made. If f of x equals mx plus b, what's f prime of x equal to? What's the first derivative equal to? Equals m. Good, Lynn. Going to equal m. And I appreciate all participation. And what would the second derivative equal? 0. Good. So when we have a line, okay, of course the first derivative is equal to the slope, m. The second derivative is equal to 0. So that means that a line has a line is neither concave up nor concave down. Okay, a line, any point on the line, it's neither concave up nor concave down. How can you decide? You can't decide, right? It's a line. So what I'm saying is for this rational function, when x is 1 or negative 1, at those values of x, the second derivative equals 0. And if you look at the graph right at those points, the graph doesn't appear to be nonlinear. It appears to be linear at that moment. I don't know if that's what I wanted to mention. So okay, are there any questions on that? Okay, all right. Well, let us continue on then. Let's see. Lynn says you can only determine concavity at intervals, not points. No. I mean points. Well, concavity. Yes, Lynn. Concavity. We think of concavity as over an interval, but we normally think of concavity as over an interval. That's how we normally think of it. Just like a function, we think of it as increasing or decreasing over an interval. Same kind of thing. So a function is increasing or decreasing over some interval. A function is concave up or concave down over an interval. That's how we think of concavity. All right, very good. Well, let us go to a third example here. So now here's a function that you've never seen before. I'm sure you've never graphed this function before in your previous classes. Okay. Take a moment to copy the example down. Okay, so all right, so we have this interesting function, y equals x to the 2/3 times 6 minus x to the 3rd. Okay, and we want to discuss this curve with respect to concavity, points of inflection, local maxima and minima. So What's the first thing we need to do? Using calculus to graph the function. What's the first thing we're interested in? Okay, so of course we have to find the derivative. And why are we looking to find the first derivative? What's the reason for that? We want to determine where the function is increasing and decreasing. That's right. Excellent, Lynn. Excellent, Joe. So we're going to go ahead and do that. Okay. So here we go. All right. So of course we're going to use the product rule. Okay. I'm going to use the product rule. Our function is x to the 2/3 times 6 minus x to the third. So when we take the derivative, we're going to use the product rule. The derivative of x to the 2/3 is 2/3 times x to the negative 1/3. And then I leave the second factor alone. And then for the second part, I leave the first factor alone. I leave x to the 2/3 alone. And then I take the derivative of 6 minus x to the 1/3. And what rule did we use here? What rule did we use to get the derivative of 6 minus x to the 1/3 power? Chain rule. Good. Good. Good, Lynn. Good, Chaco. Good, Rodrigo. We use the chain rule. And okay. So, okay, we successfully take the derivative, and I'm going to rewrite the first derivative without the negative exponents. How many remember they learned always to write their final answer with positive exponents only? How many recall that? Maybe from past classes, problems like that. Okay, Zoe remembers, and there's a reason for that. You're going to see why here. So what I'm going to do is I am going to rewrite my first derivative with positive exponents only. But now what I have in the first derivative is I have the difference between two fractions. And we learned when we looked at section 4.2, we learned that in order to find maxima and minima, we have to when we have fractions, we have to combine the fractions. Okay, I don't care how complicated the fractions are, we have to combine these two fractions. And whenever you combine two fractions, you always have to ask yourself, what's the least common denominator? Well, the least common denominator here is going to be 3 times x cubed times 6 minus x to the 2/3 power. So what I'm doing in this problem, I'm doing a hard one with you. I'm doing a complicated one with you to show you the power of calculus and to help you understand when you work on your homework what to do. Okay. All right. So I got to combine the two fractions. And so, okay, well, the first fraction, since the least common denominator is 3 times x to the third times 6 minus x to the 2/3, I have 3 times x to the 1/3 here, but I need 6 minus x to the 2/3 for so I have the common denominator. So I'll multiply the top and the bottom by 6 minus x to the 2/3 power on that first fraction. The second fraction, what's missing here? Oh, x to the 3rd. I'll multiply by x to the 3rd on the top and bottom on the second fraction. So this is no different than like adding a half and a fifth. Okay, getting a common denominator, you're using a tenth there. So, I mean, if you wanted to add 1/2 plus 1/5, you know how to add a half and a fifth. You got to get the least common denominator, and then convert the fractions. That's all we're doing here. So might look a little complicated, but if we stick to the fundamentals, we can figure it out. Okay, so now at this stage, we have the common denominator of 3 times x to the 3rd times 6 minus x to the 2/3 power, which means then that we can just write the difference of the numerators in the top. Well, if you take x to the 1/3 and if you take 6 minus x to the 1/3 and multiply it by 6 minus x to the 2/3, the base is the same, but you add the exponents. So the 1 there is because you have a 1/3. Try to make that look good. A 1/3 plus 2/3, right? That's how you get the 1 there. And the 1 over here, that comes, well, if you 2/3 plus 1/3. Okay. X to the 2/3 times x to the 1/3 is x to the 1st power, because you add the exponents. So again, we always want to think then about factoring. We always want to get it in, we want to simplify the numerator. And then we can factor a 3 out of the numerator. Okay, and so our first derivative will equal 3 minus, it'll equal a fraction with, we have 3 times 4 minus x divided by x to the 3rd, 6 divided by the denominator x to the 3rd, 6 minus x to the 2/3. One moment here. Right. Yeah. Let me put in a step here. Yep. Let me put in a step here. One moment. So 12 minus 3x is equal to 3 times 4 minus x. And so the 3's simplify out, and then that gets me down to the bottom. Thank you, Kelvin, for your question. Let me add that to my notes. Okay, are there any questions? Okay, well then let's move to the next page if we're good. So now we have our first derivative. It's in the best simplified form we can get. Time to make a chart. So we have three factors, three components to the first derivative. We have a 4 minus x, we have an x to the third in the denominator, and then we have a 6 minus x to the 2/3. Those are what I put in my chart. You see how I'm consistent. You see every problem I do, I'm consistent. Okay, so now we will get there, Ian. We will get there. So you can see, of course, that 0 and 4. I mean, based on the second derivative, why is 4 an interesting value? So for my x-axis, I put 4 there. Why is 4 an interesting value to include based on my first derivative? Why would I put 4 on the chart? That's right, Nicholas. It makes the derivative equal to 0. The numerator will be 0 when x equals 4. That's right. That's right. Okay, what about x equals 0? Why would I include x equals 0 in my chart? Right, the denominator is undefined at x equals 0. X to the 1/3, 0 to the 1/3 would give you 0. That makes the denominator equal to 0. And by the way, when x is 6, that'll make the 6 minus 6 to the 2/3 power. When x is 6, that makes the denominator 0. So this then tells me that the first derivative is nd at 0 and 6. What does nd mean, you think? Undefined. Very good. Very good. Okay. And again, from my chart comes all the good things come from the chart. So again, what I do is I look at each component of the first derivative. I create my plus or minus rows, and then the first derivative, I ascertain the first derivative is negative when x is less than 0, positive when x is between 0 and 4, and then negative when x is greater than 4. And you know how I got that based on the chart. Are there any questions on that before we? Okay. Well, then let's see what we've learned here. The function decreases. Well, where's the function decrease? The function decreases over intervals where the first derivative is negative. That means the function, based on my chart, looking at that first derivative where it's negative, function decreases on negative infinity 0, that interval. It decreases on 4, 6, and decreases on 6, infinity. Okay. The function will increase when the first derivative is positive. Okay, that would be 0, 4. That interval. So now we want to, we know where the function increases and decreases. Based on that, we're able to determine where our local maxima and minima are. So, okay, so remember now, even though the first derivative is not defined at x equals 0. Well, let me ask you, if the first derivative is not defined at x equals 0, what does that tell you about at x? I mean the function itself, right? The function itself is equal to x to the 2/3 times the quantity 6 minus x to the 3rd. So the function is defined at x equals 0. It's just its first derivative. It's not defined at x equals 0. So what's the function going to do at x equals 0? What do you think is going to happen there? There'll be, well, there's no asymptotes, Lynn, because this function, the domain of this function is all real numbers. The domain, and actually, let me go back here. Let me just add that. But we'll go back here. I mean, I didn't write that, but looking at the function, this is another. I wanted to do a complicated problem with you. You can do this problem. You can do any problem, right? But the function, the domain is going to be from negative infinity to infinity. All real numbers. You see that 1/3 power on the 6 minus x, that 1/3 power there, you can take the third power of a negative number as well as a positive number. And the x to the 2/3 power, that's just x to the 2/3 is x to the 3rd raised to the 2nd power. Well, x to the 3rd, that's that. I mean, I'm not writing this. I'm doing that. X to the 3rd is the cube root of x. Well, you can have the cube root of a negative number. So there's no, and then okay, you square a negative number, you get a positive number. So there's no restriction. The domain is all real numbers. So there's no asymptotes in the function. But if you have the first derivative not defined at x equals 0 and x equals 6, even though the function's defined there, the first derivative's not. So what might occur then at x equals 0 and x equals 6? Not an asymptote. The function would have an asymptote there, but it would have, what's this called? This kind of behavior. It's not discontinuous. The function, the domain is all real numbers. So I appreciate the participation, Kelvin. Well, inflection, we got to get to the second derivative for inflection, but there's a cusp, an infinite slope. That's what Nicholas is right. There's going to be a cusp at x equals 0 and x equals 6. Or vertical tangent, if you'd like to say. It's not an asymptote, it's a cusp. So the function has vertical tangents at 0, 0 and 6, 0. And also when at f of 0 equals 0, you'll have a local minimum because the first derivative switches. The function goes from decreasing to and then switches to increasing at x equals 0. So even though the first derivative is not defined at x equals 0, x equals 0 is still going to be a local minimum. And the first derivative, the function decrease, it goes from, at x equals 4, the function goes from increasing to then switches to decreasing. And so you're going to have a local maximum at x equals 4. Okay. But at x equals 6, okay, let me just, hold on. I kind of went too far here. Hold on. I did my circling here. Okay, and then at x equals 6, the function is decreasing, then it becomes undefined. I mean, the function is decreasing, and then when x equals 6, there's a cusp on the function, but then the function continues to decrease. So at x equals 6, there's neither a local maxima or minima. See, it's a complicated function, so it's going to have interesting behavior. Got to be a little bit careful here, class. One thing I said, I got to be a little bit careful here. There's something I said that isn't quite correct. The fact that the second derivative is not defined at x equals 6 doesn't mean that there's a cusp there. That's not correct. But it does mean that there's a vertical tangent there. So I need to take out that comment about the cusp, because you might have a cusp at x equals 0. Okay. You might have a cusp at x equals 6, but it also could mean that but a vertical tangent at a value of x, okay, does not mean you have a cusp there. You could have a cusp, but it doesn't mean that you have a cusp. All it means is the function has vertical tangents at the origin and at the point 6, 0. But I will tell you at x equals 0, there you have to have a cusp. You can say that at x equals 0, at the origin, you can say this function does have a cusp there, because the function goes from decreasing to increasing. Okay, and so there has to be a cusp at x equals 0. There's a cusp means you have a vertical tangent, but also the function goes from decreasing to increasing. So you got to have a cusp at x equals 0. But you're not going to have a cusp at x equals 6, because the function is decreasing before x equals 6, and then it gets to be vertical tangent at x equals 6, but then it continues to decrease. So that's correct. Okay, what's next? What's next? Concavity. That's right, Joe. So we got to go to concavity. Are there any questions before we get there? Any questions at all so far? Are we ready to go to concavity? May I go there? To the next page. All right. Let us continue here. Okay, well, now here's the thing. We wrote the first derivative in factored, we wrote it as a fraction in this nice form so we could produce our chart. But and the second derivative is the derivative of the first derivative. But I know that I'm going to have to use the quotient rule, and I did that for the previous problem. Okay, for that rational function, the previous example we just did, we used the quotient rule. But it's going to be easier. It's going to be easier for me just to like the I'm going to say this the right way. The first derivative, when I just did the first derivative, I had it in this form. And to get the second derivative, it's going to be easier to take the derivative of the first derivative in this form. Okay. I tried doing the first derivative. I tried taking the derivative of the first derivative in this form, and it was complicated. I didn't like it. So what I did was I went back and I said, well, let me take the derivative of the first derivative in this form. And it worked. So that's what I'm doing here. The first derivative in the first form is this. And so I'm going to take the derivative of that derivative to get my second derivative. And see, I don't have to use the quotient rule. If the quotient rule gets too nasty, too hard, I won't use it. So you have to use the product rule twice. Okay. So the derivative is the difference of the derivatives of each of these products. And that's what I have here. Take a moment to copy it down. Let me know if you have any questions, okay? We're using the product rule and the chain rule too. You know, got to remember that chain rule. Yes, yes. I will go back. Rodrigo wants me to go back for one moment. Yes, Rodrigo, you're looking at. So I'm not saying that you. Okay, all right. Okay, so after I get the second derivative, it looks like a mess, right? This looks like a mess. Well, we got to put this, we got to write this second derivative in a nicer way so that we can study it. So, okay, first thing is I'm gonna just, you know, distribute the 2/3 on each of the terms there, each of the two terms there. And I'm going to distribute the -1/3 on each of the two terms here. And then you know, I'm going to get this step by step. Now, did this take a little while to do? Yes, it took a little while to do. But I thought it would be helpful to do a complicated one with you so that when you're working on your future homework, you can just you have a little more guidance. Now at this stage, I'm at this stage, okay? Here's my second derivative. What should I do next? What should I do next? Obviously, I want to rewrite the second derivative, but I want to rewrite it with what? With think about the exponents. want to rewrite and Nicholas, you're right. I want to get to a common denominator, but I want to rewrite this second derivative so that the exponents are all positive. That's right, John. Same thing I did in the last problem, right? Right? Same thing I did. Let me just see here. Did I do that in the last problem? Maybe I didn't need to do that. Hold on. One moment. Oh, no. Same thing I did for the first derivative. Yeah, same thing I did for the first derivative. Same principles. Okay. So I'm going to rewrite my second derivative this way. Not too hard, right? Just have to keep track of things. I have now, how many fractions do we have here? The first derivative consists of how many fractions do you see for the first derivative? Second derivative, sorry. So the second derivative, I see a fraction minus another fraction minus another fraction minus another fraction. 4 fractions, right? 4 fractions. Incidentally, what's interesting about this fraction and this fraction? I can combine them. And so that's what I'm going to do. May I go to the next page? Okay. Let me know if you have any questions. You're good, Lynn? Okay. All right. So these two fractions here, we can combine them. So we'll get a -4 in the numerator. So we combine the two fractions. And so now this is our second derivative. We want to combine the 3 fractions. The least common denominator, we know there's going to be a 9. And then next to of the x portions, we have x to the 4/3 and x to the 1/3. Well, x to the 4/3 is a higher power, so that's going to be in the least common denominator. And then the 6 minus x to the 2/3 here, and the 6 minus x to the 5/3 there. 5/3 is the higher power, so that's going to be in the common denominator. I mean, how many recall getting least common denominators this way, looking for the higher power? Maybe you did it in pre-calculus or even before then, but That's right, Lynn. I agree. I think this is the simpler way to get the second derivative. I worked this problem out just like I were a student, and I didn't like, I just worked it out, and I didn't want to mess with that. I wanted to get the second derivative this way. So the least common denominator is going to be 9x to the 4/3 power times the quantity 6 minus x to the 5/3 power. So I'm going to then multiply each of my three fractions on the top and the bottom by what I need to multiply by, so that the denominator will be 9x to the 4/3 power times 6 minus x to the 5/3 power. So I think for the first fraction, it's easy to see. I got to multiply by the circled expression there. For the second fraction, well, I have x to the third in the denominator. I need x to the 4/3. So I'm going to have to multiply. I'm going to need an x to the first, because x to the first times x to the third is x to the 4/3. And then, because I have 6 minus x to the 5/3, well, in the denominator, I have 6 minus x to the 2/3. To get 5/3, I got to multiply 6 minus x to the 2/3 by 6 minus x to the first power, because 2/3 plus 1 is 5/3. I'm having faith that everything's going to work out nicely. You have to have a little faith when you do these problems. Okay. Okay. So then the last fraction, well, I'm missing an x to the 4/3, so that's why I multiply by the circled expression. Okay, so like I said, if you can do this problem, you can do any problem. Even if it's something a little bit new, you ought to be able to handle it. Okay, are we ready to move to the next page? I want to rewrite now my second derivative. Oh, actually, I'm not ready to go to the next page. I'm just going to go down here. Lynn's good. Okay, here's my second derivative. All right, so I combine all the numerators. Now, how am I getting a 2 here? How am I getting a 2? Well, the 6 minus x to the third times 6 minus x to the 5/3, 2. Well, I add the exponents. A third plus 5/3 is 2. Okay, and then I think here, the second part, x times 6 minus x, I think that's easy enough. And then the x squared here, if I take x to the 2/3 and multiply by x to the 4/3, 2/3 plus 4/3 is 6/3. And so I get a 2. Are there any questions? Okay, may I go to the next page? All right. Now let me ask you, this 6 minus x quantity squared, of course, that's 6 minus x times 6 minus x. We're gonna FOIL that, right? And when we do, we're gonna get 36 minus 12x plus x squared. Right? We're going to FOIL that 6 minus x quantity squared. Okay, we'll get 36 minus 12x plus x squared. And that's what I have written here. And I multiply all that by -2, of course. Okay, and so nice things happen here when we multiply out the numerator. Some nice things happen. Yeah. 24x's cancel out. And we have a 4x squared, but we have a 4x squared, but we have a negative 2x squared and another negative 2x squared. So those go out also. Giving us then negative 72 for our second derivative. We got negative 72 over the denominator, 9 times 6 minus x to the 5/3 times x to the 4/3. But the negative 72 and the 9 simplify, so you get negative 8. How about that, huh? I'm going to think that's absolutely amazing. Oh, you're right. A good catch. Thank you, Lynn. Right, there should be no 9 in the denominator. Good catch, Joe. No 9 here. Fix that on my notes too. Now what happens, I'll tell you, the textbook, this problem corresponds in the textbook to, let's see, it's section 4.3, example 3. No, example 5 in section 4.3. But they tell you that the second derivative equals this, but they don't show the steps. They just state it. And it's because they want to save paper, you know, and they figure, well, the students can figure that second derivative out. But, you know, hey, I thought it was a nice thing to do to show you how they got that derivative, that second derivative. And now we're ready to make a chart. I might go a few minutes over. If you can stay, I mean, it'll be in the recording. If you can stay a few extra minutes, I'd be grateful. If you can't, I understand. But if you can stay a few extra minutes. So here's the second derivative. there it is. And there are three, well, there's one. Oh yeah, the 9 shouldn't be there. Thank you. Hold on. Let me, hold on. 9 just should not be here. That means the 9 should not be here. So in the chart, the 9 should not be there. Thank you. Okay, and so it won't change though the results. Thank you. Okay, and so let me just see here. One moment. Let me fix this right now. Okay, and so we have, well, we got a -8, we got a 6 minus x to the 5/3, and we got an x to the 4/3. And they are all here. Okay. And you know how to make the chart. And so of course this is our x-axis. And we're including the values 0 and 6 because those are the, the interesting values. And you know how to make the chart. You know how to do that. So the second derivative is not defined at 0 or 6. Okay. It's not defined at 0 or 6. The function's defined at 0 and 6, but the second derivative is not defined at 0 or 6, which makes sense because if you have a vertical, if you recall, we discovered that we had, based on the first derivative, we discovered we had vertical tangents. The function has vertical tangents at x equals 0 and x equals 6. So the concavity won't be defined there. But concavity does change the second derivative changes from negative to positive about x equals 0, and that means no, I'm sorry, let me take that back. See, I'm rushing, and let me do it again. The second derivative is negative when x is less than 0, so the function's concave down on -∞, 0. And then the function is concave down on 0 to 6. So that means that the that means that 0, 0, which is a value, the function equals 0 when x equals 0, that's not an inflection point because the concavity did not change. Okay, so did not change. Concavity, the function is concave down on -∞ to 0 on that interval, and then it is concave down on 0 to 6. However, at x equals 6, the function changes concavity from negative to positive. What I mean is the second derivative changes from negative to positive. Therefore, the function goes from concave down to concave up. And so there is an inflection point at 6, 0. So before 6, 0, before that point on the function's concave down. But after 6, 0, the function's concave up. All right. And the next step now is just to take all that information and graph the function, which I'm going to do on the next page. Are there any questions? We're almost done here. Thank you for staying. All right, let's get to the next page. Okay, here's the function. Here's our function. It's graphed, and you can see the function from -infinity to 0. The function's decreasing and concave down. And then there's that vertical tangent at x equals 0. Then the function starts increasing, but it stays concave down. It stays concave down. Okay, the function increases all the way up till x equals 4. Then you have that local maxima at x equals 4. The function starts to decrease, but stays concave down. Then when x equals 6, the function has a vertical tangent at x equals 6. But then what happens at x equals 6? What happens to the concavity after x equals 6? The function becomes concave up. That's right. So this is this function here, you've never seen it. How many is this the first time they've ever graphed a function like this? How many is this the first time they've ever graphed a function like that in their life? Yeah, and we did, and we used calculus to help us graph the function. See? Calculus is very powerful. And this is an important function. I mean, maybe an airplane is flying like this. Maybe well, no, hopefully not, right? But after 0, 0, maybe the airplane does this. I mean, you gotta know where things are concave up, concave down when you're dealing with I was just thinking in my mind, like an airplane, I think we'd be very interested if this were the path of the airplane. I think we'd be very, very interested in how many remember just from, unfortunately, when there are airplane accidents, they study what the airplane does, its path. How many see that in the news? They use radar to figure out what the satellites to figure out what trajectory the plane took. How many recall that? Yes. Well, I can think of this as a very good example. I mean, we don't want to think of planes having accidents, but you know what I'm saying. So concavity, important. Hey, it went from concave down. I mean, you see what I'm saying. Are there any questions? Okay, I'm going to stop.